Sunkara, who's at Berlin, hands-on approaches to understanding dynamics of hybrid models.
Thank you, thank you. Can everybody hear me? Or should I move this up a bit higher? Everything okay? Seashells by the seashore. How much wood can a woodchuck chuck? A woodchuck chuck wood? Everything clear? Lovely, lovely. So, thank you so much for the invitation and giving me a chance to talk here. And I've really been looking forward to this particular talk because of like the mix of people who have come. And so I've actually spent a lot of time thinking about what do I want to tell these people. And I realized what I wanted to talk to you about is not methods in particular, but like the things in between, which nobody ever writes about in papers. Like the intuition behind the methods or the intuition behind the mathematics. And like this is the stuff which, if you're somebody who is like a novice and starting off in this field, you probably will be like, why on earth did he go from A to B? And hopefully this is going to give you some insights on this kind of middle bits. And so the pipeline that we work with in Berlin is the classical, like what everybody does, is that you start off with some model. And then you kind of have a look at that model, you try to understand it, you do some analysis, you try to work out its patterns, and then you find some kind of numerical scheme which exploits this, such that you can then quickly compute the model to do some kind of inference down the line at some point. So today I'm going to be talking about like this part here in the middle, analyzing the piece of model somebody has given you. So someone's already given me this model, right? The parameters are given, everything is given, it's just here's the model. And then we kind of want to see how to actually understand or intuitively think about this piece of object. So these are the stuff we're going to be talking about. Don't be too scared. It's not so bad. So it won't be, seriously, it's not. So the type of processes or stochastic processes that I'm always interested in look like this. And I call these Kurtz processes. And this is a bit embarrassing having the fellow here sitting in the front row, right? But there's a reason.
As long as you spell my name correctly.
Did I spell it wrong? Oh, no, okay.
That would
Yeah, I know, right? That would be like double embarrassing. Oh, God. So these are the processes that I'm interested in, and I don't want to reduce them or anything. I just want to understand these themselves. And I personally think they're actually quite beautiful in the sense that you have a population or a vector of populations, and events are happening via some Poissonian unit Poisson process where the rate at which these are firing is somehow a function of where the system is. And how much this particular reaction perturbs the population is given by your stoichiometry. Alpha k's here are my propensities, and then omega is my state space. So my process is somehow like a trajectory which passes through my state space. And what I do then is that, because I'm not a stochastic analyst, I instantly take this process and shove it into the Chapman-Kolmogorov equation, and I get the chemical master equation. And everybody has talked about the chemical master equation. I want to kind of reiterate, but kind of look at it in more detail. What does the chemical master equation actually say? It says that the flux, the probability of observing a particular state at a particular time, the derivative of this is nothing more than being somewhere in an adjacent state and transitioning in to this state that you're going to see, minus that you're already there and you're going to leave it, right? It's like such a simple equation, and this is why it pops up everywhere. Like there's a master equation for every equation. Because it says, I'm here, I'm going to go, I'm not here, I'm going to come. Yeah, it's easy, it's nice. But it has computational challenges, because that means what you have to know is where are you and where you're going to go. And this is the challenge, or the cursor dimensionality, and all these kinds of weird terms start to come up, because what you do is you pile all these equations together and you construct a simple ordinary differential equation. But the only problem is that this A, this matrix, I like to think of it as a giant matrix, is large, right? And it's the size of how many states you're going to see, yeah, because it tracks over all these states. And so what people do in terms of now the numerics is simply go, okay, I have this particular initial value problem, and I have this generator A. Maybe this generator A has some property. So I'm going to take my A and I'm going to project it somewhere. Well, this is what they do. They go, oh, maybe it has some kind of smoothness in certain things or blah, blah, blah. So they take it and they project it, let's say into like a wavelet domain, or they do it into polynomials or radial basis. All they do is that they take this A, they project it somewhere into another space, hoping that in this other space, imagine like you had a diamond and you only knew what to do with a square. So you take your diamond, you do a rotation, I'm like, okay, the square is kind of cool, I do all my stuff on the square. But then the problem happens is, do you know how to turn it back into a diamond? And this is kind of a bottleneck for a lot of methods. And as I said, I think in workshop we should also discuss open problems. And I think this is a really nice open problem. A lot of people talk about doing transformations and doing some sort of projections, but then when you want to come back, this is an actual real open challenge. Like, you've done something, you've reduced it, but now when you pull it back, you somehow don't have a you cannot always guarantee that you have a probability. You can't even guarantee that it's a solution sometimes. It's like, wow. So this is it, right? This is what everybody solves. This is what somebody, if we want to apply this is what you will be doing. So I don't want to look at any numerics. I just want to look at this Kurtz process, and I want to understand its properties. Right, sorry, I'm just going to always look this way every time I say it. I'm going to like turn myself this way. So I want to understand just the properties of this, right? Forget about numerics. And one of the really nice properties it has is, it's called the finite state projection method. It was written by Munsky and Kamash. There is Kamash. He has disappeared. Okay, I think he's giving a talk later. But he introduced this as a numerical method, but actually this is not a numerical method at all. This is a property of the generator, which is generated of this Kurtz process. And the method, okay, I said method again. The property is something like this. Let's say ahead of time you accept some error on your density epsilon, ahead of time, a priori. If this is true, then what happens is, what you can do is, let's say you're starting off with E, you can choose some states in your state space, and then you can form like a little boundary where instead of extending it out, you can reconnect it all. You reconnect your domain, like particular region, and you point all these states into something called a sinc state, right? And if you do this, and then you evolve this particular generator forward, what the property of the generator is that your true probability, right, non-reduced, is always bounded below with the solution that you have, and bounded above, bounded above by the solution plus the probability which is in the sinc. So this is a property, this is not a numerical method. You can do this for any system. If you pick your domain, if you have some sort of prescribed epsilon, you can always kind of draw out a region and then evolve it, and you know precisely the error window within which your true solution exists. And this is a really important property, right? So I think I would like to scrap that part at some stage. I'm sure if others would also agree if they were here. So let's just have a look how this works, okay? So this is the boomerang example. You're going to see why it is called the boomerang. But it's a really simple chemical system. So you have A being created, B being created at a constant rate, like it's just a birth process. And then A and B come together and then they annihilate each other. Why? Because it's fun. The process looks a bit like this. You start off with 5 copies of each. Then this is the annihilation propensity. It's quite simple. And then each species being just created at the rate 1. It's quite nice. So let's look at a really nice video. Here what I'm going to do is I'm going to draw like a simple contour plot so you can kind of see how the density travels over time. Here what I'm going to do is I'm going to put an x every time I used a state in my equation. Right? And we can kind of see how this propagates over time. So let's have a look. The contour has no scaling, by the way, so it's just for you to see the shape. Don't panic. And it keeps on going and going, of course, and what happens is it keeps on going into a nice big boomerang. This is also known as Vikram's banana in Berlin, but let's not go into those details. Maybe after a beer I'll explain. So this is quite nice, right? And I didn't do any numerics. This is just the property of the Kurtz process, which I'm just exploiting, right? So there's more properties that this process has. And another one is that what you can do, somehow your state space, you can decouple it into large strings of paths. You can decouple each of your states. So therefore what you can do is, let's say you're in a particular region, you can calculate an upper bound for where you're going to go. And if you have an upper bound of where you're going to go, then what you can do is you can do simple branch and bound kind of strategies. And then what you can do is you always can predict what your support is going to be through time. Right? So this is, once again, a really natural property. It's called the gated one reaction domain expander. I was young when I wrote it, so it's just, names are long and less creative. And similarly, you can also reduce the domain. And how you reduce the domain is using this particular idea called the best n-term approximation. So what you do is you take your probability, you sort it in a descending order, and then you go to the tail and you throw away, let's say you want to throw away tau. You throw away the biggest set you can find, which sums up to tau, and then whatever you get left over still like sort of is a valid solution to your master equation. So you have a strategy on how to grow, and you have a strategy on how to reduce. And I have done nothing special here. I've just taken the master equation and just like fiddled around with it, and then this is the properties, which just fall out naturally. So now let's have a look, another animation. Let's see what happens if you can grow and sort of shrink the domain over time. Huh? So I look at a simple SIR. I keep the populations of S plus I plus R fixed, so that's why I made R redundant. Also, this makes a better 2D graph picture for you guys. So I start off with 200. Susceptibles, 5 infected, and this is my transmission, transmission? No, transmission, yeah, transmission, sorry. I was thinking a car. Anyway, this is my transmission propensity. This is my infection, my recovery propensity. Just give me a second, guys. I'm going to pull through together. So same story again. What we have is the support here and some kind of density. And let's watch. Let's watch. So this is just the system. Oh, by the way, all these simulations are in real time. This is just. I was too lazy. I just videotaped it using QuickTime. So it's just. I think the most amount of time which is taken is to render this thing. And also the error, the global error is 10 to the minus 6. That's why you're getting this really nice long tail. And you see, then after a while, because you allow for some error, you start to lose these states, and whoosh, there it goes. And blah, 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 blah. Funsies, huh? So, okay, I think that's enough. So, when somebody gives me a particular model, right, so the first question I always ask is, what's the minimal support? So people always say, it has that dimensionality, it has 10 different dimensions, but actually, for a given prescribed error, what is the minimal support? Because what's actually happening is that you can imagine the density is kind of moving around. And let's say you had like a huge string where you had A goes to B, goes to C, goes to D, and you only had 10 particles. This actually has no cursor dimension. If you just take its minimal support, it'll just be a really simple thing, which is flying through your state space. So a really important question is to ask is, how big is your minimal support as soon as somebody gives you a particular model? And then, if the minimal support is, let's say, in the order of tens of thousands, this is simple. Yeah? The system is quite small. You can solve this on a regular system using some method. If, let's say, it gets really big, we want to know then, okay, what on earth is happening? Why is it getting so big? Right? And so to understand why it's getting really big, we have to understand what's happening on each of the dimensions. So let's talk about splitting now, right? Okay, so once again, to explain this sort of idea of splitting, I'm just going to use two variables, x and y. I'm going to say x is something that I'm interested in, and I want to split away y. I want to summarize what's happening in the y direction with respect to what's happening in the x. So then what I do is I take my propensities, I put this assertion, it's not really necessary, just the math looks a lot neater, right? And then I can also split my stoichiometries into just components which are acting on x and components which are acting on y. Nothing really special. then what I assert is that I say, okay, my joint probability of x and y, I can rewrite it as a marginal distribution in terms of x and a conditional probability of y conditioned on x. I assert this. And then I assume that P1 is somehow is a probability, and then P2 is somehow like a valid probability. And so what I've done is I've reduced now, so I have this x and y, I've reduced it to an x and a whole family of stochastic processes, which are each one is conditioned on each of the x's. So if you think about it, remember if we had our x and y, it's like I fix my x and I build a process which goes up and down on y, or it's doing something on y, yeah, for each of the x's that I'm kind of looking at. This is really important, so keep this in mind. Yeah, we're going to come back to it right at the end. So if now what I want is I want to study this, right? So if I want the equations for P1 on how to construct P1, or I want to understand what is P1, what I do is I just take the product rule of that with respect to time. And then I get the top condition, and then I sum over y, and then this part here becomes 1, this part here by our assumptions becomes 0. And then, so it says, if I have this sort of splitting, and I only want to study one part of this system, all I have to do is to know how its marginal density evolves over time. I just simply have to sum the master equation over all the other dynamics, like over all the other things which I don't want to observe. Nifty idea, huh? So let's keep doing it. Yeah? So P1 is equal to that. Then what I do is I sub in the master equation in. I'm using this notation because it's a bit easier. Yeah? This is a shift minus identity operator, so if that goes through, it's not so. So first I change the propensities. Then I sub in my definition that I wanted for the joint probability in terms of this marginal and conditional probabilities. And then if I sum in all the y's, this is the term that I get in between. So now notice, this is really nice property. If I want to study just what is happening in terms of in the x dimension, all that I need to know about jumping sort of left and right in x is that I need to know the expectation with respect to your propensity of the probability distribution that is happening in this direction. That's all that I need to know. If I know this one number, no, I know exactly how precisely I can jump left or I can jump right. This is all that you need to know. So really, the only information you need to know in the y direction is this. And now you can imagine, I mean, I'm not going to tell you how to compute this, but every single numerical scheme that you see, which is a hybrid method, is nothing more than estimating this in one way or another. Each one is just nothing more than another estimate of this. Either they do one thing, either they estimate the process within in that direction, or they estimate the integral, one or the other. And this is what we can reduce everything, like, you know, every single hybrid process down into. It's all about where you are, how are you going to describe what's happening in the other direction. No? So let's get some intuition for this, and I'm going to quiz you later. So I thought I'd just give you a heads up, so you better pay attention in the next set of videos, right? Okay, so this is like for us to gain some intuition, right? So I'm going to do the boomerang again. I'm going to let A be the one that we're interested in, and we're going to look up slices of A in terms of B. So this time I'm going to look up this slice, and what I'm going to do is I'm going to take the joint probability and divide it by the sum of the probability in there, which gives me my P2, my conditional probability distribution. Yeah? And I'm going to plot that here in this second one. Is that cool, guys? Now let's see. Let's see what happens. We can see as the density kind of moves through this kind of line, it starts to kind of stretch out, and then, I mean, the density is still moving more and more along this line, so we get this stretching. Has it stopped yet? No, it's stopped now. Cool, huh? So now let's take another point. Instead of here, let's kind of pick something more along here. Yeah? I think this one was 18, 16? 16, I think. Let's look at this. Notice here, it kind of reached steady state really quickly, right? I mean, like in terms of with respect to this line. Because you can imagine, it's being pulled like this. If I look at anything In this region, the density is still moving up that particular line that you're watching. But down here, it's pulling in the horizontal direction, so it reaches. So the amount of, if you think about this in terms of, let's say you want to write an estimate or you want to do some computation, a lot of effort will be required here to estimate that one number that you need to understand how you're going to jump in A compared to here. And we can kind of see that in this next one. And by the way, just apologize, it takes some time because these are, there's no analytical solution, so these are all like numerical. So now what I'm going to do, same thing, but I'm going to plot here the conditional expectation down each of the slices, yeah, over time. So let's have a look at this. I can see down here, stabilizes really, I mean, like it moves up, reaches equilibrium, and it just kind of stays there. There's no other information which is required. But then on this side, somehow the density is moving in that direction, and it's still sort of changing through time. This is important. Yeah? Just gain intuition about it. I'm not telling you something like profound. I'm just asking you to build a feeling for this because, as I said, you'll be quizzed later. So similarly, this is a really nice example. People, because I read lots of papers on people trying to do hybrid methods for SIRs. And what is really funny is that it has this particular property. I'm going to show you now. Check out what happens. So this is also the conditional expectation. So I is what we consider to be like what we want to summarize. S is what we want to know, like the jumps from the left to right. And so let's see what happens. Notice here, it's like barely changing at all. And what actually happens is this line here, I mean like over here, of course the probability starts to kind of go up and down in this region. But here, the system is predetermined. And it's predetermined on where it starts. So you actually need nearly no computation about, I mean, no information is needed in this direction once you know this. Because it's fixed. I mean, it's just the density flies through it really fast at this particular angle. It doesn't shift up and down. It just goes. And then, of course, as soon as it runs into the wall, then you get more dynamics because then the density is moving in sort of weird ways. And then some effort is required. Now, similarly, so once again, another example. Now, let's say we take it the other way, right? Let's say the susceptibles, I want to summarize, but the infected, I want to understand the jumpings within too. And then let's look at the perspective I want to look at is, let's say, down 100. Let's see what the conditional probability is going to look like if I evolve this process down 100. So, of course, what's going to happen is first I'm going to get my first peak as the density approaches my line, and then it passes through. And then here comes the painful part. Ta-da! You can imagine if you're writing a numerical method and your underlying density does that, you kind of want to cry and form a little ball, because this is, I mean, to estimate something like that is a very difficult thing, unless you actually have the full bimodal density. So it's all, so you can see, I mean, any, how do I want to put this? How do I want to put this? I don't know how I want to put this. How do I want to put this? Okay. So the idea really is when you want to do a reduction or you want to understand the effect of one dimension on the other, it's really like you fix one dimension and you look down that particular path, and then what you're interested in is how your density is passing through this particular, I mean, I'd like to think about it as like you have bundles, and in one dimension you have some sort of simple jump process jumping between the bundles, but then you have something else like a transport equation which is moving up and down the bundle. And what the moving up and down the bundle is nothing more than the density traveling through it. And if you have a system where the density just goes like, whoa, wiggles right through all your bundles, then this is going to be a really difficult thing for you to estimate. I mean, like to estimate what's happening in that direction. Whereas if you look down and then your density just passes through your bundle without ever crossing it again, this is something quite easily approximatable. And this is what I mean, like when a lot of the times, people come out with these papers and they go, oh, we found the best estimate. I'm like, because there is nothing happening. Your bundle passes, I mean, like your density passes through this bundle. There is, okay, I don't say it that way, but I think you know what I mean. All right, so now it's all to do, so hence it's all to do with this. How we estimate this is all that we're doing in any sort of numerical approximation. And so let's say Jeff, do we actually have a Jeff before I, no, we don't have a Jeff, excellent. So let's say Jeff walks up to you, right? And he gives you a model. Can everybody see this? Yes, you can see this? And then, so this is X. I don't know how to do a bold Y. I think it's this way. Okay, yeah, got it. Okay, this is X and this is Y. And so Jeff comes up, and then he gives you a model. Sorry. Which is doing this. What happens is, you look at its density, and all it's doing is moving. Okay, done. It's moving left and right, right? Maybe in the beginning it starts off somewhere else, suddenly goes somewhere, and then it just moves left and right, left and right. What sort of approximation would you use for estimating this particular thing? This. Anybody? Sorry? Yeah, exactly. This is Y. What would you do? Imagine, if it's just moving left and right, what are the conditional expectation? What's the derivative of the conditional expectation? 0, because it's not changing anymore. So if you actually reduce it down, it would become a quasi-steady state approximation, right? This is kind of what would happen. Now let's say Jeff kind of went away, he was happy with that, and he came back with another problem, because Jeff does that. All right? And now, he gave you something like this. It's increasing, but in a sort of diagonal fashion, right? It's kind of going up, but let's say it's going more up in that direction than in this direction. Yeah, let's say it's more like that. Okay, Jeff gives you this. So now, what would you want? How would you want to estimate this? Anybody? Anybody? I think Simon talked about this. I think, what did he call it? I don't know, I forgot what it was. Simon Cotter on the first day? Constrain something or other. Something or other. Anyway, in other literature, it's called the model reduction by conditional expectations. Because for each of these, you can find a conditional expectation which will completely summarize the dynamics in that direction, right? Now, Jeff was not happy with both these answers. He comes up with something a little bit different. He gives you something like this. Okay, it's doing something, but it's also growing in this direction. But it is growing such that the mean, how do I want to write this? I don't know how I want to write this. Let's say the variance of, I'm going to screw this up, yx of t is somehow of the order, okay, I'm running out of space, is somehow of the order of 1 on the expectation of that. So that means, the expectation is blowing up, but the variance is shrinking, right? What could you do in that kind of scenario? Wow, failed, sorry, guys. What you can do is just a system size expansion, right? You can do a system size expansion, and then you'll get an estimate for this with respect to that. So see, at the end of the day, this is really what it all boils down to, your reductions. And I remember Andrew was saying, I don't know how to prove how my method is working. So this is what you do, Andrew. This is to you, is that you calculate this. You'd say, what is your estimate? And then you subtract this by this. And then if you plug this into the Gronwell lemma, it will get exactly the error in your first marginal. Because this is the only difference. This is the true thing. This is what you put in, right? And the difference of this two will, let me just go back. Sorry, videos. Yeah. So then you would have like another equation on this side, but in this red thing, you'd have your thing. And if you have this kind of equation, I'm sure Kevin will tell you, what you do is you use the Gronwell lemma. Wouldn't you, Kevin? Yeah, see? Easy, easy, yeah? I mean, like, what do we stress about? I mean, like, life's good. Yeah, come on. But of course, I mean, this is, as I said, I've only talked about 3 particular styles of approximation which already exist. And let's say another one which might be really interesting is, let's say, somebody gives you something else and you're not too sure. What you can do is you can do a simple, like, PCA on your data points, and you find the transformation which might make it into something simple, into like sort of components which which have particular nice approximations, then you can do that. Or the toughest part, which once again I'd like to talk about open problems. One of the biggest open problems is what happens when this beta is something which is not mass action. When you have that case, remember how I showed you, it suddenly had this bimodality? This does happen when you have especially Hills type functions as your propensities. We have no idea how to tackle these things. Like, how would we estimate this? I mean, you could sample it, but this is really expensive. But nevertheless, at the end of the day, all we are doing is estimating this particular number so that we can reduce and understand a part of our Kurtz process. Sorry again. And as I said, I've done no approximations anyway. This is just the pattern. This is what these beautiful stochastic processes have as a natural feature. So I thought, I saw some people doing some pictures on single cells. So I thought, so what we actually do, what we get paid to do in Berlin is, like, we're investigating the degeneration and maybe even therapies of osteoarthritis. And this is kind of a little component I just wanted to kind of quickly go in. And of course, osteoarthritis is the degradation of this particular piece of cartilage in your knee. Well, in all things, we're interested in the knee. What happens is, at some point, you are running, you do a slide in your awesome soccer game thing that you do, and then you rupture something, or you have some kind of damage, and then the pain kind of goes away. But over time, what happens is your cartilage is degrading really, really slowly, and your body is compensating because it's happening so slowly. You don't even notice it, you keep compensating. And then suddenly, one day, I don't know, you miss a step on the stairs, and you go down, and then all the cartilage rips apart, 2 bones touch, you're screaming in pain. So this is a serious issue, and like with an aging population, it's really important for us to know how this degenerates and if we can regenerate it, like within the individual. So this is what we work on. It's kind of cool, huh? So we have these really, really, really complex models where we have like some kind of extracellular matrix which is consistent, which contains some collagen and proteoglycans and some other protein complexes. And then what we do is we apply forces to it, right? And as we apply forces to it, the cells which are inside this cartilage feel this force. And then what happens is they change their phenotype. And then they start to restructure. They start to produce some more collagen or some more proteoglycans, or maybe they even destroy some just to balance it out. And then, of course, that changes the extracellular matrix composition, which then changes how the loading is taken, and then that changes the phenotype. And then this sort of cycle is what we're really interested in modeling. And of course, the reason why I brought all this up is this particular feature here, which seems like a lot of people are interested in. And so inside a single cell, I mean, what we want to know is how long is a particular gene turned on for? A simple question. How long is a particular gene turned on for? And which gene is turned on for based on what sort of binding is happening on the receptor? Right? This is kind of a classical problem I think everyone's interested in. So what we did is we kind of brought this ideas of hybrid methods to this thing. And what happens is, even though like you have all these really complex reactions in between, but most of them are really simple. And so if you use this philosophy of looking down a particular direction, if I'm only interested in like if a receptor binds or doesn't bind and gene expresses or not expresses, the things between it actually stay pretty well on their bundles. So I can simplify this entire complex system to nothing more than information about this, and some information in here, like some things I might keep. Let's say some reaction has like a dimer or something like that. It's really hard to simplify something like that. So I keep a few, but everything else I can summarize because I can estimate that expectation of what's happening in that particular direction really well. And so I think this is sort of similar to what you guys are doing, and it's something maybe you should also consider doing. I think that's why I put up this slide for you guys. But to explain this, I mean, I don't want to do the full thing, but I want to use an example which Dave showed me last year, and which I think is really nice in explaining or visualizing all the stuff that I've been talking about. The model looks a bit like this. So you have some template, and this template produces some DNA, and this template also produces some structures, and then at some point this DNA will somehow go into inside the structure, and you get a virus. The challenging part, of course, is that the timescale separation is quite interesting. So T goes to G, and then of course G then go back to T. This is okay. But then notice like this sort of structure. So T can produce structures with a propensity of 1,000. This is a bit of a pain in sort of if you run a regular simulation, right? And then the template can die, the structures can die, and then at some point at a really, really slow scale, a structure and a genome can come together to produce a virion. And in these kinds of problems, one of the things, I mean, in the pharmacokinetic wing that I kind of sit in, what we're interested in, how long does it take before one virus gets made? Or the probability of the virus. Because then what we do is we put a bit of drugs in and we kind of see, does this window increase or decrease? So the two important things here are the templates and the virus. So now let's have a look. Is this system actually as, I should probably mention, if you think of the minimal support of this, it's massive because of this reaction in here. Yeah? This blows up. And it's massive. But just because the minimal support is big, is the density actually complex on this minimal support? Or can the information be summarized? So let's have a look. So I'm going to look down T. Let's ignore V for a while. Yeah, just look down T. So let me fix T. And I'm going to look down T. Let's see what reactions look like on G. So the reactions involving G are 1 and 2. And if T is fixed, this is nothing more than a birth process. And this is nothing more than a death process. So if I look down here, all that is happening is a birth-death process, whichever step I take. Yeah? Similarly, if I look at the structures, if I look down T, all that is happening is, once again, birth-death, just much faster, reaches equilibrium much faster. So if I want to know how T is changing, I mean, like jumping around, I know so easily because I know what the birth-death process does. I mean, this is kind of understood. So an easy approximation is just to do that. And of course, I'm ignoring 6 for a reason, because I'm going to show you the error induced by it. So let's just say I ignore these 2. And I set my approximation to be the expectation of the birth-death process along each of the lines. No? So if I do this, let's see what the overall expectations look like. So then what I do is I take the expectation of the individual random variables. And these are like sort of some stochastic simulations I ran a lot and then just did some bar plots. And this blue line, there's also a green line, just ignore it from now. I stole this picture from a paper, my paper luckily. So you can kind of see the templates are in expectation, are approximated really, really precisely. And because I'm only looking at templates and virons, my state space is about 200 states. No? Because there's only about maybe 12 templates, and the number of virons until here is maybe another 10 or something like that, or maybe a bit more, but it's not so big. And then you can see I get a really nice reconstruction of the expectation of the templates. I get a really nice reconstruction of the genome. It's not a surprise, because I just showed you why it happens, because in the directions, there's a density there. It's wide, but it has a nice shape and symmetry, which you can summarize. Right? And now we can see the same thing for the structures. Ta-da! It estimates all this. And now here, this is what, let's say this is something I was interested in, how long it takes, the probability of a virus one virus being made over time. If I look at that, you see, there is some error here. I said, ignore the green thing. Just, there is some error, and this error is induced because of the last reaction that I miss. So it's not a perfect birth-death process going up. There's also a bit of leakage, which is going out from just the death of from this reaction. So I take this out, therefore I overestimate how much S and G are there. Therefore, I overestimate how fast I'm going to produce a virus. No? It's acceptable. I mean, it makes sense. It's not acceptable. It might be acceptable. Who knows? But it's nice, right? I mean, I haven't done anything special. I've just exploited the inherent structure of the density and just looked at the reactions and tried to find like a particular pattern. And these things, this computation takes a fraction of a second. No, probably not a fraction of it depends. It doesn't take a long because it's only about 200 equations that you need to solve over time. Cool. So, so that is that. I mean, I hope you guys sort of gained some intuition. Like this is like the middle part, as I said. If somebody gives you a model, I think it's really important to understand what is actually happening inside the model, because the numerical experiment the numerics you're going to choose is going to bias your inference. So if you're not exploiting the structure which is existent within it, how do we know what's kind of happening in the inference section? So now, how much time do I have?
Minutes?
Sorry?
A couple minutes?
Couple of minutes? Oh, okay. Okay, I wanted to give you an open problem. Actually, yeah, how about I just introduce the problem and then we can chat about it later. Yeah, is that okay? Okay, so this is an open problem. I believe workshops are more about talking about like the middle stuff which people miss and open problems so that we can introduce some discussion. So let's look at this open problem which me and Stefan Engblom from Uppsala have been working on for 2 years and we have no solution yet. And maybe it's something that you've also thought of and maybe you're smarter and you've actually solved this. So imagine you have sigma is your parameter in your parameter space and omega is some piece of data. I use L omega sigma as my likelihood of my data given my parameter. Mu is some prior distribution, nu is my evidence, and pi is my posterior distribution. This is not so special, right? Now, the tough question is, let L star be an approximate likelihood, right? We never ever really know what the true likelihood is. We always at some point, we approximate it. So let L star be an approximate likelihood. And of course, a lot of the cases, what we have is this, is that our approximate likelihood, the error is somehow proportional to the parameter that we have chosen. Right? And now, if I want to do a parameter inference, I want to construct, if I construct a posterior with my approximate likelihood, what does that mean? Like, what is the error? Like, how can we write down the error? Especially if it is a function of it, and if this function is not computable. What is it? How can we check if what we produced is somehow valid? And can we write something down? So this is an open question. I'm happy to discuss over lunch. Thank you. I'd like to leave. I actually wanted to finish early, but it seems somehow I saw a Seinfeld gif, so I thought I'd add my own. Questions? Anybody?
So in my mind, when you do hybrid modeling, you can just reduce it down, to stochastic discrete modeling formally, stochastic continuous modeling formally. And I think that, as Andrew was suggesting, you must explore just simply the number of molecules in the system that will take you from one formalism to another, but also the propensities. And I was trying to figure out how exactly what you were discussing applies not only to the number of molecules as an important parameter for making a decision on the modeling formalism, but also on the ultimately how fast the reaction events are in your system.
Yeah, exactly. So the way it is where the propensity is in the function. Okay. Go away. It's this part here. See, this expectation, your propensity is kind of weighting the density, right? So let's say it weights it in such a way that it kind of comes in really close, right? Then this is great, because this means it's easily estimatable. But let's say it's such that it kind of spreads out the thing a lot more. Then, yeah, this is a problem. Like this would need more effort to estimate something like that. It's exactly so. So it's exactly what I kind of mentioned, is that either we work on this or we work on this, and of course, sometimes you have to work on both of them. Yeah. Yes. Yes.
So I can well see that for these relatively simple problems, you can develop this intuition, you know, how you can sort of integrate out certain degrees of freedom. But if you start with, let's say, the full complex network, right? How do you go about it in practice, right?
So how
do you get insight into this dynamics, you know, what you were explaining?
It's exact. So we know some particular results, like monomolecular reactions, like when they take in a particular input, they will stay monomolecular. No, sorry, no, 1 second, let me reply. A density which starts off, let's say, unimodal, if you pass that through a monomolecular set of reactions, it's going to stay that way. Right, so you have these kinds of pieces of it. So then what I do is I look at my cascade, and then I start to circle where sections which I know first will take in something nice and give out something nice. So this is stage 1. And then at stage 2, I look at particular sections which might not do this. And then I try to look at, okay, will they actually change my density in such a way that I'm going to get something a bit complex or not? If it is, then I will leave it as it is, because then I can handle it. It can be something weird, and then that feeds into the rest of it. So this is, the intuition is like you look at your reactions, and you think about the marginal of the variable which is about to go into this reaction, and this is like a systematic way of doing it. And then
for, let's say, these birth-death processes, I can see how this goes. Also for dimerization, right? It's also a famous example.
Yeah, exactly.
Can you go much further? I mean,
at the moment, we're only sticking to in this particular intuition style, I'm sticking to mass action kinetics. But one of the things, as I said, we don't know yet how to deal with these when we have Hills type functions. Okay, this is important, but we don't know yet how to. There's no intuition on how one comes in and one goes out. But the idea is we want to do it for those two. I mean, Michaelis-Menten is still okay. Somehow this works. Magic, I don't know why yet. But Michaelis-Menten is okay. As I said, polynomial mass action is okay. Hills, still don't know how a density is morphed through going through a Hills type reaction.
Let's stop here for lunch. Please join me in thanking everybody.